Okay, just a little correction. Here, I thought it should be like below, but 13.6 is still above. And when we consider breaking the bond, we mean like here's the molecule, and to take this to break up this molecule, right, from like H2 plus to 1H and another ionized H. There's like one with electron and the other without electron. The amount of energy you need to pay is like 2.65 experimentally. And that means this E star is going to be minus 13.6 minus 2.65. So I got a little bit mixed up, but it is below 13.6. Any questions or comments? Here is a like exercise. Consider total energy of like P states. E total is equal to V ion of R, which is unchanged, plus E of P as a function of R, and explain if bonding is possible. So, like, is there a minima? Okay, you can follow exactly the same argument. All you need to do is just find these two limiting energies. One is again 13.6, but the other one is P state, right? And P state is not 13.6, and like compare it with this, and the result is not obvious, but there should be no minimum and there will be no bonding for the P state, which is like simple consideration of energy accounting. Any questions or comments? So this was the simplest molecule, and the next simplest molecule is hydrogen molecule. So now in this case there are like two ions and two electrons. And we have to like consider, is bonding stronger or weaker with two electrons. Like a rough estimation is like, if like suppose these two electrons are completely independent, right? Each does what it does, and for each there's like a minus 265 molecular bonding energy, and another one minus 265 molecular bonding energy. Maybe the total is like what? Minus 5.3 eV. So this one ignores electron interaction. And it turns out like electron interaction is going to increase this value. Right? So experimentally, E total for hydrogen is equal to a little below this. I mean, not awfully different, but still a little below this. It's like minus 4.5 eV. So not minus 5.3. And R star for two electrons is equal to 0.074 nanometers. Okay. So for 2 electrons, we need to consider indistinguishability. So the total wave function of 2 electrons has to be symmetric or anti-symmetric. So complete wave function. Let me use uppercase capital psi 1 and 2 is going to have a usual orbital part psi 1, 2, and let me use some sigma 1, 2. These are just notation. So this one is, let me call it orbital, and this one is spin. So the orbital part can be symmetric. We have 2 options. Orbital can be symmetric, then spin part should be anti-symmetric because the total wave function has to be anti-symmetric. Or orbital can be anti-symmetric, then spin part has to be symmetric so that total uppercase psi is anti-symmetric. So let me write that. Psi 1, 2 is symmetric. Let me call it psi 1, 2 is equal to psi some symmetric 1, 2. Then spin sigma 1, 2 is going to be sigma. Let me write it. These are all notations to write down what we mean. Don't be worried, right? So that total psi 1, 2 is psi symmetric 1, 2 and sigma A 1, 2. Yes.
In above, you wrote the experimental value was not consistent with the theoretical value. So,
it's not theoretical, right? This is very simple-minded. Like we are saying that like we have like these 2, one can be here, another can be here, and if I put one more electron, this one more electron is going to do exactly what we thought one electron would do. But we know this is not the case, right? These 2 electrons, first they have to have Pauli exclusion. That's why we are considering the spin. But they also have electron-electron interaction. So that's why it is actually reasonable that the difference is there. But even then, as you can see, the difference is not gigantic, right? It seems like electrons effectively avoid interacting with each other too much, right? And they still obey the Pauli principle. How does this come about? This comes about because of like this spin and orbital part being consistent with each other. So this is one option. The other option is psi 1, 2 can have anti-symmetric 1, 2, like this p orbital we outlined in the previous case, but sigma symmetric in 1, 2. So since we understand the orbital part, psi s and psi a are just s and p orbitals we just considered in the first lecture, let's focus on spin part. For example, let me write a couple of like symmetric spin wave functions. For example, 1, 2 is, it can be, for example, this. First electron is up, second electron is also up, right? And if I exchange, 1 is up, 2 is up, so it's still symmetric. Or they can be both down. This is 1, 2. Or I can also do the following. I can, 1 is up, the second is down, plus the second is down, the first one is up, down, the second is up. This is 2. Right? This is also allowed, right, because of superposition in quantum mechanics. So these are what we call triplets. And so these are symmetric parts. For the anti-symmetric part, there's only one, and it is 1 over root 2. One can be up, the second one is down, and minus, one is down, and the second one is up. And now if I exchange, right, wherever you see 1, write 2, wherever you see 2, write 1, you are going to see this function goes to minus of itself. And this is what we call singlet. If you want, these are like, these are parallel spins. Of course, parallel in the sense we write here. And this is anti-parallel spins. So this is where we cannot solve the Schrödinger equation exactly anymore, and unfortunately what we have to do is like, right, we have to solve the Schrödinger equation and see if there is like a minima or not. For the simple ionized hydrogen we can do that, but for hydrogen molecule we cannot do that. And we have to appeal to like numerical solutions. And let me just tell you what the numerical solution says. So this is energy, and this is R, and so this one is parallel spins. Let me call it H up. Maybe I can call it E up, and the other one is something like that. So this is anti-parallel spins. And let me call this E up down. And this is the solution that I outlined. So here, this is the energy we said. It's approximately minus 4.5. And the corresponding radius here is like approximately 0.7 angstrom, which is R star. There's like a peak, there's like a dip, right? There's like a minimum. If there's like a minimum, molecule can go and find that local minimum and be stable there, right? If there's no local minimum, that means there's no local configuration that the entire molecule can just settle. And here we are the detailed numerical solution. Actually, it is not very complicated, but I wanted to keep it a little bit simpler for you. The result is like when the electrons are parallel, there's no bonding, right? There's no local minimum. And this actually comes from the fact that if you have two ions, one here and another there, and you want to put a bonding in between these two, and if you want to put electrons in the same bond here, right, because of Pauli principle, they have to be like this. Whereas if they have the same spin, they have to avoid each other, and the configuration can be here and there. But that's going to be a repulsive case, right? There's like a net charge here, net charge there, and they are going to repel each other. For these two ions to stay together, you have to put the glue in between, not outside. And to see this quantitatively, we have to solve the Schrödinger equation, which is beyond this course. That's what I'm saying. Okay, let's consider more complex molecules. What this means is molecules with more than 2 atoms. So typically, like as you have more and more atoms, it's going to be more and more complex. But we have like, again, simple principles. And the simple principle is like any bonding, any effect is going to be limited in the outer shell. All bonding happens between outer electrons. So you can forget the core electrons. And actually this is suggested by X-ray spectra, right? Last week we talked about X-ray spectrum. and the X-ray spectrum of, for example, carbon atom, like X-ray of carbon atom is independent if you look at the carbon in one compound or another compound, right? If this carbon is embedded in like a more complicated material, it's going to have the same thing. If this carbon has like one molecule or another, it's going to have the same X-ray spectrum. And that means the core of the carbon atom is unchanged, right? That's what X-ray is probing. And all the bonding, all the molecular stuff is happening for the outside electrons. X-ray of carbon only probes inner core, and it is independent of molecular structure. Then we have to think about molecular orbitals and bonds for like higher and higher shells, right? This is the message. Okay, then we need orbitals for higher shells. And let's consider all of these. The first one is, okay, here is, so this is X, Y, Z, and this is, for example, 1s orbital, right? This is 1s, and I'm going to put plus on the entire shell to indicate that the sign of the entire sphere is not changing as you go from one side of the sphere to another. So this is 1s. There's also similarly 2s. Let me actually consider 2s. 1s is kind of irrelevant. So we can consider 2p, but there are like different options for p. So this is, let me call this, this is what I call px. And one side here is, if this is plus, the other side, as you go from here to there, the sign of the wave function is going to change. Just like here, right? For example, you go from here to there, the sign is changing. The same thing happens there. So this is px. I can have a p along y, and I can have a p along z. So let me also draw that. I can have, so this is py, and this is pz. And the sign I chose here is like plus or minus, and this is plus or minus. And if you go back, I think we also showed this a little bit when we were studying hydrogenic orbitals. For example, this one is 1 over root 2 psi ml is equal to 1 plus psi ml is equal to minus 1, right? Each one of these were like kind of like a donut, and we said if we combine these two donuts, we are going to have a dumbbell in x, y, or z direction. And similarly, the second one, so this one is going to be minus in between, right? Whereas this one is going to be, ml is going to be 0 here. So there is 3 options. Now we imagine bringing 2 of these orbitals together, right? There's like one atom here, another atom here, and we like bring these 2 together, and we have to imagine how these orbitals modify as they come together, exactly like in the 1D case. And these are called molecular orbitals. Molecular orbitals. For example, I can consider bringing 2 s orbitals together. There's like, for example, an s orbital here and another s orbital here. So this is, if you want, this is 2s, this is another 2s, and they go to something like that. I don't know, they turn into some elongated sphere, and okay, let me push this just a little bit. And what we call this is like this is S, and because, okay, you imagine an axis that connects the two ions, and if it is symmetric around this axis, we are going to call it an S state, but a molecular S state, and molecular S state is demonstrated with Greek letter S, which is sigma. So this is so-called S sigma molecular orbital. Okay. I mean, a lot of terminology, but it is not complicated. It is exactly what we learned for 1s, but in the molecular case. We can do exactly the same thing for example, let's call this direction to z direction, right? The direction that connects two ions is z. Then I can consider approaching these two guys, right? This is going to be 2pz, this is 2pz, and this is going to be plus plus minus minus, and when I bring them together, okay, let me copy that, cancel that, what is going to happen is like I'm going to have like a more electron in between, and I'm going to have these little ears here, because these two are going to combine and accumulate in the middle, and what we call these is like there are two p orbitals, right, pp, but because it is still symmetric with respect to a z-axis that's going through the two nuclei, it is still sigma bond. So this one is, if you want, S is L is equal to 0, but here L is equal to 0, but molecular angular momentum is 0. This is L is equal to 0, that's molecular angular momentum is 0. That's why we are using sigma rather than S. The next example is, let's consider one more. For example, we can consider this one and this one, right? This is going to be two. Okay. It can be y or x, but let me choose x. This is 2px. This is 2px. This is plus, plus. This is minus, minus. And when they combine, so this is going to be, okay, let's erase these ears. What is going to happen is, like, you can see there is like a vacuum in between, and you have to preserve this empty space in between. So what's going to happen is like something like that, and something like that, right? So here's electron cloud, and now we are going to call this a pi bond, right? So this is plus and this is minus. As you rotate, the sign is changing. This is we are going to call this pp pi bond, because now angular momentum is 1, molecular angular momentum. Yes.
Is there a reason you put the same poles for PZ close to each other?
So in this one,
Yeah. The plus.
I mean, if this is plus and this is minus, it's going to be destructively interfering, and there will be 0 and there will be no bonding, right? So the atoms, of course, total orientation is like arbitrary, like any orientation is fine for the atom, but when they come together, they are going to bring their plus signs together so that they can bond. Like if you bring one plus with the other minus, it's going to be the reduction of amplitude in between. It's not bonding, right? So that's why I brought it.
Don't they repulse each other if the same poles are at the same?
So it is not like, so this is like kind of like this overlap in the single model, right? So in the single val case. Here we said there has to be some overlap here and some overlap there. But if you flip one of them, there'll be zero in between, right? Exactly the same thing. And you don't want that for bonding. We want more electrons in between the ions if we try to form molecules. Okay, any questions or comments? So it seems like we are preserving the molecules and atomic orbitals and they form, but what happens is actually the atomic orbitals with different L can also, right? I can, for example, combine S and P, for example. Here, let me give you an example for that. So example is water, H2O. So oxygen has Z is equal to 8. And if you look at it, it is like 1s2, 2s2, and 2p4, right? And here I have 3 orbitals, put up, 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 and there's 1 down. And what we should do is like, so there are like, let me try to draw this, like this is X, Y, and X, Y, and Z. So you can see there are like 2 unfilled orbitals here. And what is going to happen is like we have like PX. Okay, let me use a different color. There will be a lot of things. Maybe I can do it a little bit thin like this. So one like this, another along X, and maybe another along Y. And now I'm going to bring 2 hydrogens, right? And the hydrogen is going to have 1s, and I have another hydrogen. This is also 1s. So what we do in H2O is like you bring this hydrogen to this bond, another one to this bond, right? But because these 2 hydrogens, okay, electrons are shared between these orbitals, but there's still the hydrogen ions, and they are going to repel each other. When they repel each other, this angle between these 2 orbitals is going to change because of the Coulomb interaction between ions. And what will happen is like, let me pull this here and maybe pull that guy here. And what happens is something like this, like there's like oxygen, and there's 1 hydrogen here, another hydrogen here, and the angle is like something like 104.5 degrees. Good. So in this case, you can see we are combining 1s and p orbitals to form the bond. Okay, there's like one last thing, and this, for me, the most interesting thing. Let me also explain that, and I'll finish it there. Something called hybridization. If I can spell this. And this generally happens with carbon, right? Let's consider carbon, and Z is equal to 6. And what we have is like 1s2, 2s2, and 2p2. And here you can see I have to fill 1 here, and I have 1, 2, 3, 4 available spots. And if you remember, okay, here's the question from last week. What is the energy of 2s state corresponding to 2p state? Which one has the lower energy? So energy, look, let me E2s compared to E2p. Which one is bigger? Are they identical or different? Based on what we discussed last week? Lower, right? Why? Yes, right. Because smaller angular momentum leaks inside the nucleus a little bit more, and if it leaks more, it means there's less screening. If there's less screening, it's going to have smaller energy. So typically, ES is less than 2p. Now suppose I'm bringing other atoms, and typically I bring hydrogen or other carbons to this carbon. And because now this electron has one carbon here, right? Suppose you are 2s or 2p electrons, there's one carbon here, another carbon here, and it's going to get confused between screening. Is it going to screen from this carbon or this carbon? What is going to happen is, because of the presence of other atoms, it can also be hydrogen. These 2s and 2p are going to be roughly degenerates. Okay. Due to other atoms, E2s is going to be roughly E2p. And if they have roughly the same energy, that means they are going to have an opportunity to hybridize. And there are different kind of hybridizations. What is going to happen is you are going to take these 2s and 2p, and you are going to have so-called sp hybridization. For example, we can do sp3 hybridization, sp3 hybrid. So what you can do is you can take one wave function from 2s plus some px, some py, and some pz. And for overall normalization, you are also conclude 2. And by all possible signs, for example, this can be minus, plus, plus, this can be plus, minus, minus. There are in total 4 different combinations. So what is happening is you take an s orbital and you take a p orbital, and it's going to give you something like that, right? And this asymmetric, there's a rabbit ear, single ear, and it can be in any directions, right? Right? But there are because of 1, 2, 3, 4, there are 4 different possibilities.
I didn't understand what happened to carbon when you were explaining.
What happens to?
Carbon.
Carbon? So right now, yes, that's what I'm trying to get. So there are these orbitals around carbon, and there are other atoms, either hydrogen and carbon, and these 2s and 2p orbitals, they modify due to presence of other atoms. And they are energetically more or less favorable, comparable. And for example, what we can have is something like, I think I didn't write it here, but for example, we have CH4. I think this is what? This is called methane, right? Is that methane? Yeah, right. So this is methane and not CH2. In the hydrogen case, right? H2O. But in the carbon case, we have something like that. And this one is going to have these ears, if you want. So there's this tetrahedra. And each edge of tetrahedra is a, so this is H, this is H, this is H, this is H, and there's oxygen in the middle, right? This is what we call sp3 hybridization. Similarly, it doesn't have to be just like this. For example, we can have sp2 hybrid. In that case, what happens is 1s and 2p, let's call them px, and py hybridize, but pz is unchanged. So that's what sp2 hybridization is. And this is the interesting one, at least for a physicist. What is going to happen is like, okay, these three orbitals, they are going to have like these three ears. Maybe like I can put it like that. One is like that. Actually, let me write the larger ear and skip the little ear. There can be an ear like this. There can be an ear like that, and there can be an ear like that, right? So this is planar. If you want, there's like smaller pieces like that. And each one has like 120 degrees. And the remaining PZ orbital is going to be free. Like it is going to do what its own thing, it doesn't matter. And this is, for example, what's happening in so-called ethylene. Ethylene. This is C2, H4. So this is C. So this is H. Each carbon has like three neighbors. Or it is also happening in benzene. I think this is C6, H6, and it is something like that. So this is a nice hexagon. I cannot. This is okay. Let me try to. Okay, each of these is like a carbon, and you connect each one. Right, this is hydrogen. So each carbon has like again three neighbors, but there is like one free electron which we show with like this ring. So like benzene is like a plane. Among the plane, there's like a circular free electron hanging out on top and at the bottom. Right, that's what we are imagining, and that's electron is like here. This electron is shared. It doesn't belong to any particular carbon or hydrogen. It is shared by entire system. It's like what we call delocalized.
This is the free PZ.
Yes. The free PZ is doing its own thing. It's like not contributing the bonds. And there's also like something called polyacetylene. And it is, I think, I don't have its chemical formula, but it is something like that. You have these carbons. And okay, this just keeps going from minus infinity to plus infinity. There are like hydrogens hanging out here and hanging out there. And for example, in this case, there's like 3 electrons are contributing in the bonding, and 1 electron for each carbon is free. And this electron, for example, turns out to be like a emergent relativistic electron. It's just like, so it obeys Dirac equation for free electron. And if you are a physicist, anytime you see Dirac equation, you get excited because you have an opportunity to study relativistic physics, relativistic quantum mechanics, without going to colliders. And another one is graphene, and that's, let me make this my last. So this is graphene, and that's one of the one of the most influential research areas in both theory and experiment in the last 20 years. And what's happening in graphene is something like that. You have these hexagons, another one here, another one here, and so on. So each one is C, right? It has like, because of sp2, there are like 3 neighbors for each graphene, but there's still this free Z orbital. And this free Z orbital just delocalizes, right? I don't know how to show it. Delocalized Z. And this gives so-called Dirac cons. So this one was a Dirac equation in 1D. So this is 1D Dirac equation. If you want, you can study one-dimensional relativistic physics in this material, whereas in this there's like 2D Dirac cones. So if you look at E of P as a function of P, you are going to see these Dirac cones. And for a really long time, it was thought that like this was not possible for some reasons that doesn't concern us. People, like very influential people, thought that was impossible to exist in nature. But in, I think, 2002, Andrei Gaim and Novoselov, they produced graphene, like a single layer of carbon atom, and the way they did is not like something like crazy experiment. So they basically used a pencil and they used like a tape. By basically taping in and out repeatedly, they isolated a single layer, and then when they look at their like tape with a microscope, they showed presence of a single layer of graphene. Right, it's like a perfect single atomic thickness without any hassle. Of course, it is not so easy to produce. And then they did transport measurements on that material to show these like Dirac cones and other interesting properties. Okay, maybe I can stop here. Any questions or comments? And continue next time. Okay, thank you.